Okay, everybody, let's get started. So, launching straight into it, can I get everyone's attention? Thank you kindly. I'll just let everyone get their seats. It's one of those days. Thank you for coming out here in the rain. Okay, so I'm going to launch straight into it once I just adjust this a little. So yesterday, we looked at a couple of important things that are interesting because they make a lot of our coding better, they make a lot of our coding easier and faster, but they're completely sort of, actually I don't want to say non-technical because they're not actually non-technical. There's a lot of technical stuff in code style. But it's the kind of thing that people often overlook because there's no kind of hard and fast rules about everything. There's a style guide and there's an attempt to adhere to a style guide that a lot of people are going to push towards. But there's sort of varying levels of success you're going to get with it, as opposed to with your functional code. With the functional code, sometimes it's really obvious whether it works or not. Code style, it's harder to gauge whether it works or not, because sometimes it's a matter of how much longer did this take me to solve a problem than it would have taken me if I'd written my code a different way. So harder to gauge whether it's successful or not, but in terms of how much effort that we put into our work and how much time we have to put into something in order to get it done by a deadline, code style comes in very, very important. That wasn't English, was it? Comes in very handy in that regard. We also had our first look at functions. That was sort of me just dropping a lot of the theory about functions on you. So we haven't done a demo of that yet, and that's not the last time we're going to talk about functions. So I'm going to show you at least one function in use today that we're going to use to work within the code example I'm going to do today. The other thing, though, is I'll probably go back over functions next week again, and we'll get deeper into it as well. But I wanted to at least sort of drop the idea into your heads at this point, and then we'll cover it again later. There's a few things that are going to be like that during the course, where I will introduce something, and I'll probably reintroduce it a couple of times, depending on the level of the topic itself. So some things are more confusing, and you want to see them a few times. Some things are less confusing, like, say, if statements. I think that people can reasonably understand if statements without me needing to teach them again and again, except you're obviously going to see them again and again and use them a few times anyway. All right, so what are we looking at today? I have spoken a little bit about the idea of what a computer is. So the idea of a computer being this combination of a thinking bit and a remembering bit. I just want to make these things as simple as possible because the theory is actually quite simple. And when we talk about these in a technical context, we're thinking about a processor and the memory in the computer. And all of our programming is based on that, right? We're going to give instructions to the thinking bit and get it to do stuff like basic maths and stuff, decide whether to go into an if statement or skip an if statement, that kind of thing. And we're going to ask it to remember things by doing things like declaring variables and stuff like that. We're going to go into a little bit more detail into what the memory is this time. And we're going to think about actual memory, and we're going to think about one of the main ways that we use memory on a computer, which is arrays. Arrays are groups of variables, basically. I'll tell you more about it because we're going to go through it in detail. So we're going to go through how we use groups of variables in C, some of the intricacies of how they work, and an example today of us putting it all together so that we can learn a bit about that. Okay, so as I was saying, at its most fundamental level, if we want to look at only what is theoretically exact about a computer, it is made up of two parts, and these parts are spread out amongst all the different physical bits of the computer. So your graphics card has these separately, your processor has these, you can think of your motherboard having this kind of stuff as well. It's always going to be one thing that executes instructions. So one thing that says, I've been asked to do this, then I've been asked to do this, then I've been asked to do this, and I just do them in a particular order. And then something to save the information between those things. So the idea of, if I do want to do some calculations, I expect that every time I do the calculation, I'm probably going to save the results of the calculation somewhere in my computer. We're going to refer to that very widely and roughly as the computer's memory, and I'm not being too specific about that. You know, when you get sold a computer, you get told the memory is the RAM, the random access memory, but I'm just considering everywhere that we can store information on the computer to be the computer's memory. So some of it lasts longer, some of it lasts less time, but it's all just saving bits. I want to talk to you about a hilarious yet fundamentally super important theory, which is, actually it's not even a theory, people have built these. It's known as the Turing Machine. So if you remember from, I think it was the very first lecture, I talked about someone called Alan Turing, who we consider to be the father of modern computing because he was there creating the first computers, the first digital computers, I should say. He's the father of digital computing. He had a theory of a kind of a computer that existed as a roll of tape. So tape then being considered just a piece of paper. So we can have a piece of paper that could be infinitely long in either direction. So it's just this one big long piece of paper. And then a thing that can move back and forth along this piece of paper. And it just says, I can write a 0 or a 1 anywhere on this piece of paper. So I can just move back and forth, writing a 0 or a 1 anywhere on that piece of paper. And in that thing that moves back and forth, there's a little bit of a memory for what it has done and where it's up to, as well as a set of instructions that it's going to carry out. So you can see the two fundamental bits, right? There's the memory as the piece of paper that stretches off in either direction. And then there's the thinking bit, which is the thing that says, if I read a sequence of 001 or something like that, then I'm going to overwrite some part of it with another 1 or something. You know, we can have something that processes a set of instructions and it remembers where it's up to in the instructions. In the same way that our computer, when we're running programs, remembers which line it's up to in the program and says, okay, this is what I'm going to do next. So we've got some... Oops, I skipped. There you go. We've got some examples of this here. So I've taken these from Wikipedia. There's a really, really complicated example if you wanted to actually try to build this. That's like a mechanical specifications of this tape with holes in it so that you could roll the tape back and forth. And what they call the head, which is the thing that's going to read or write to the tape. I think that one's based on like a magnetic tape. So that's pretty old school as well. I don't know if this thing's ever been built in this particular configuration, but I've seen people do it with like woodwork and a pen that can draw onto the paper. But my favorite one is this one, which is really funny. So this one is a person sitting inside a box, and the box has wheels, but it can only roll back and forth on this ground. And with them, they've got a piece of chalk, and they can draw on the ground a 1 or a 0 wherever they walk. So they can go back and forth along the ground, drawing 1s and 0s, and in their head, they can remember the set of instructions they're going to do. So all they have is the ability to follow certain instructions, move back and forth along this memory, this space, which could be any size. In our computers, this space would eventually run out because we've got a limit to how much storage we have on a computer. The theoretical Turing machine doesn't run out of space, so it can just go off in either direction forever. A lot of our programming, we actually kind of treat our memory like it can go forever. So when we say int x, that's us saying, okay, I need a certain amount of space on the tape. And we never really check whether there is space or not. We just sort of assume it's available for us. We assume that the computer is going to provide us with enough space to be able to do things. The funniest thing about the little person inside the box, walking around and writing stuff on the ground, is functionally that is identical. Well, not identical, but it has exactly the same capabilities as all the computers you're using right now. There's actually nothing that our computers can do that without enough time, this thing can also do. So any kinds of calculations, any kinds of programs or anything, you can put a person in a box, have them walk back and forth along a really long line, give them a set of instructions, they can write their instructions on the inside of the box or something like that, and they will be able to execute any program that we can on our computers. It might take them several years to actually do it, because I can't imagine walking back and forth and just like, even with like say 10 bits of data, I'd be back and forth for a few hours just trying to get, one thing written out to a terminal or something like that. But theoretically, this thing can do everything that our computers can. So when we boil it down to that simplicity of that, that allows us to sort of think about our programming in a different way, where all we're doing is making some decisions on what we're going to do, and we're going back and forth along that tape, and the memory in our computer is actually laid out exactly the same way as this tape. It starts at one end and just counts upwards. And it doesn't matter how big your RAM chips are or anything like that. It's just looked at as one long string of ones and zeros that you can use in chunks. So when we are looking at our computers and comparing our computers to something like a Turing machine, our computers do much the same thing. So the CPU is the little person in their little cardboard box, wheeling it back and forth across a playground somewhere. They have a set of instructions, and we can consider the programs that we write for our computers to be that set of instructions, and they're going to follow them one at a time. And they're going to follow them. The computer's going to follow them exactly. We're going to hope that the little person in the box is also following their instructions exactly. And that CPU, everyone's heard of what a CPU is, right? It's kind of like the brain that's in your computer. It can read and write information to the memory on the computer in the same way that the little person walking backwards and forwards in their box with their piece of chalk, they can write numbers on the ground. So they can erase the numbers they'd seen before, and they can put new numbers there, that kind of thing. The idea of having the instructions and remembering where you are in that, in C programming, when we run our C programs, the programs know what line they're up to at any particular point in time. You'll know this because if you ever press Control-C in your program, it should probably, not always, but a lot of the time it'll tell you what line it was on when it last stopped. The instructions for the Turing machine are our lines of code. And any kind of reading or writing we do is what we do whenever we say this variable equals this, or use this variable somewhere. I do a printf and I say %d, comma, this variable. That's the variable that I'm reading from. So those things are like us asking the person in the little box to walk up to a certain area, read some information, and do something with it. Memory, and I was hinting at this before, there are different levels of the ability to remember stuff on a computer. This is where we delve into, this slide. I can talk about this slide. We could probably talk about this slide on its own for a couple of years. Some people in this room are potentially going to be on this slide for most of their degree. So those of you that want to go into, actually, is anyone here doing computer engineering? Yep, there's at least one. There's a couple back there and stuff. Okay, so you're going to know more about this than I do by the time that you finish your degree, because I'm not a hardware person. I'm much more a software person. So when the hardware breaks, I ask someone else to fix it. But from my limited knowledge of this, I know that every time we store data on a computer, there's multiple places that it can be for different uses. So people may have heard of the idea of CPU registers. CPU registers, so the CPU itself is a chunk of silicon, about yay large, that sits in your computer, and it's the bit that does the thinking. So it's the bit that crunches the numbers, follows the instructions, makes decisions, that kind of thing. It has a little bit of memory on it. You may have heard it called the CPU cache, and it comes in different levels. There's like a level 1 cache, which is right next to the CPU. There's a level 2 cache, which is in the same physical space as the CPUs. Is there more than level 2? I can't remember. I don't know. I'm sure that every time someone brings out a new CPU, there's different subtleties in the design as well. So that is the fastest bit of memory, and then our CPU can just use that back and forth. The only downside to it is if you turn off your computer, all of that memory disappears, because the CPU requires power to hold those things together, but they work really fast. If you want to keep larger things than what the CPU registers can hold, we use our random access memory, which is like the RAM, the memory that you get sold for your computer. So this thing here has got like 16 gigs of RAM. Most people in the room will have probably 16 gigs of RAM sitting there. Some people have probably splurged and they've got 32 gigs of RAM. I don't know who really needs 32 gigs of RAM, but maybe if you're, what are we doing? If you're doing 3D modeling or working on film or something like that, you use a lot of RAM. But the memory here is slower than what's in the CPU, but the only reason it's there is because it's cheaper. So it may be slower, but you can get a lot more of it and still have your computer affordable. And then we have the hard drive itself. So the hard drive or your SSD or anything, this is the only thing that stays saved once the computer turns off. So everything else requires power to hold what it's doing, and we would consider to be like temporary storage of things. So this is where our programs go when we're running. They go into the memory, and then they go into the CPU registers exactly in little pieces as they're going to be used. But where we save our files and stuff is on our hard drive. And the trick there is, again, it's much slower, but it lasts longer. So there's this constant trade-off with the way that we build computers to get as much space as we need to hold things, while having the space we need to be able to run things as well. So there's a little, every now and then I will introduce, because this is an introduction to not just programming, but computer science in general. So I'm going to try to like drop in snippets here and there, things that could be much more important to you later on. So if anyone's heard of the operating systems course, I think that's one of the first steps into learning about this stuff. I think if you're continuing on to, I think it's 1521. So I think a lot of people probably have 1521 on their timetable for later on in this year. You'll learn more about this kind of stuff there. I hope it's 1521. It's either that or no, it's not 1531. I forget. There's a lot of these different course code numbers, and they're confusing to me as well, so I'm sure they're confusing to you. Anyway, so this is the memory, and every one of these pieces of memory is actually the same as that one long string of tape. So all it is a whole series of bits that can be zeros or ones. That's it. There's nothing more complicated. I mean, there's some complicated stuff in it in terms of the physicality of it, the way that it's built and stuff like that, but the way that we think of it theoretically is it's always just going to be zeros and ones that we're going to use in some way or another. So going on to C itself, when we are actually programming, this is what's happening under the hood. So the source code files, so whatever .c, what were we looking at? That bad code style .c that I did, or the dice checker .c. Those files are going to be saved on our hard drive. I think everyone's reasonably familiar with getting stuff on a hard drive because you can open up whatever file explorer or whatever you have on your laptops right now, and you can see all the files on your hard drive. So they're organized in a way that we can understand them. If we want to look down into the nitty-gritty, your SSD has a whole bunch of zeros and ones in it, or your hard drive has a whole bunch of like little magnetic cells on its spinning disk, and they turn on and off, and they're bits. Somewhere on that, our C program is sitting there, encoded in a whole bunch of zeros and ones, so that we can see what letters were typed in, and we have an exact copy of it every time we need it. When we compile our programs with DCC, DCC creates another file. So we've seen this already, right? Every time we run DCC, we can look in that folder and we'll see another file which will have the name of the -o, whatever word we put after the -o when we compile. If you don't put the -o, you'd have another file there called a.out, which is the default compiler output. That file is also just a series of zeros and ones sitting on our hard drive. The difference between that one and the one we write in C is the one that we write in C is very human readable. I mean, You may not think so at the moment because we're still learning how to read it, but that's the human readable version. And DCC compiles it into something that you can, if you want to, on your computer, you can literally double click on it and then it runs. So that's the program, that's the instructions at the level that the computer wants to see them. When we actually do double click on that, or if we're in Linux, we do / and we write the name of the program that we're going to run, the first thing our computer does is it grabs everything that was on the hard drive, copies it into the RAM there so that it can start to use it. So it takes it from this kind of long-term storage, puts it into the short-term faster storage so that we can read and write to it really easily. Our CPU, our little person in the box on that piece of tape, will then line itself up with the first instruction, and it will walk along and read the zeros and ones for the first instruction and say, okay, this is now what I'm going to do. So it's like it will go along that first instruction and then write its first instruction into its little list of instructions, maybe inside the box. I'm just sort of extending this analogy of the person inside the cardboard box now. And it will go through and it will say, okay, I'm going to follow these instructions one at a time and I'm going to make them happen. And every time we say, I would like to store a variable, it says, okay, I'm going to go along to a piece of tape that we're not using for instructions, and I'm going to mark out 32 bits on that piece of tape, and I'm going to remember this is where the integer dice one size is. So when I go back to my instructions and someone says, look up dice one size, I know where to go in my tape to read it, that kind of thing. So in your computer, all the memory is kind of being used like that. We're storing stuff in the memory, and then we're going to go back and access it, and we're going to read it for different purposes. So some of our memory is used for our actual instructions. We're going to read those in order to do things, although it's not always in order. Or we get something like a loop. We'd read that in order, then we'd go back to the start and do it again until the while loop fails. It's check, that kind of thing. And then our variables are going to be somewhere in our memory as well. Every time we read or write to variables, that little person in the box has to walk over to wherever the variable had been and read it or write values to it. Going into a little bit more detail about what's happening in memory is every time our program begins, we will be given a certain amount of memory. I think the standard starting point is about 2 gigabytes worth of memory, but it can expand based on how much you use. Later on, I'll show you a demo of us using a lot of memory. But that's once we get into the depths of actually learning how this works. We will usually get a program set up a bit like this. So I will get a chunk of memory, and this memory is just in a vertical stripe like this. So I'm considering this to be a piece of tape with zeros and ones in it. I've just lined it up vertically here because it's easier for me to put it in a slide. So somewhere we're going to have our instructions. So this is our compiled code. So after we've run DCC on our code, it turns into instructions that our computer can read. They have to be in memory somewhere for my computer to be able to read those instructions and run them. So part of my memory is going to be that. I'm also going to have some space for variables. So any variables that my program knows needs to be created, they'll be there. And then we have 2 other bits there, known as the heap and the stack. We'll talk a little bit more about the stack later, and we will be using the heap later. You don't really have to remember their names or anything, except later on, if you do any low-level computing, like compilers or memory and things like that, you will actually sort of use this. So the stack here says where we are in our program, so it's going to remember, in a sense, what line we're up to, but it's also going to remember which part of the program we're in. So as we get more complex, we're going to be running different functions, and the stack's going to remember which functions we're inside or outside of. It's also going to remember which file we're working in at the moment, so the more complex we get in programs, the more we're going to start using multiple files for our programs. And then the heap, which is above that, is initially empty space, but as we run our program, if we ask for more space, that's where we're going to put things. I'm going to teach you later how we explicitly ask for more space, because there's ways in C, this is one of the reasons we teach C, is it's a language where we can actually manipulate that space in memory. Most other languages, you just ask for something and your computer deals with it. With C, you're going to deal with it, which will hopefully teach you a lot more about what happens when we actually use memory. Okay, so I've spent just under half an hour telling you a theoretical concept of a computer and a whole bunch of stuff about hardware and things like that. I've glossed over a whole lot here. So obviously, you don't necessarily have the capability now to physically build a computer from scratch and how it works and stuff like that, but you could probably build a Turing machine if you wanted to. You get a bunch of you together and like a cardboard box that someone's thrown away from like getting a fridge or something like that. You could actually make a Turing machine. This might not be the best use of your time, but it could be a lot of fun. Hopefully this gives you enough information so that you've got an idea about what your computer is actually doing when you're writing C code. But there's a lot more here. As I said, even just one of those slides. So this slide here, we could spend a couple of years on this slide and how we set things up and how computers use memory and stuff like that. People obviously have spent several years doing this so that we can have something like this where when we write our C code, this magically happens in the background and we don't have to think too much about it. Likewise, this kind of thing here, people have spent years and years on this kind of thing to make sure that all the computers you have there are both functional and affordable at the same time. And this comes down to hardware design. And they have hilarious issues where the physical distance between these two, so we're talking about a few centimeters in your computer, is actually affected by the speed of light for how fast we can get information back and forth between these two. And that depends on which CPU cycles, with these things running billions and billions of times a second, which CPU cycles you can get information to and from these in is based on the physical distance between them, how long it takes these things to get stuff. All of that stuff is within the field of computing. And again, that's years and years of study if you want to go that deep into it. Right. So the thing I wanted to talk about today, which is where all this theoretical stuff is leading, is arrays. So arrays are actually big chunks of memory. In fact, I could say anything. Our instructions, our code that we run is also big chunks of memory. Every variable we've ever created is a big chunk of, it's a small chunk of memory, but it's still a chunk of memory. Let's talk a little bit about why we're going to have arrays first, and then I'll talk about how we put them together. So sometimes we're going to want multiple variables that are the same type together. So they're going to represent multiple components of a particular thing. And sometimes we want to be able to process them all under some kind of umbrella. So they're all together in one kind of unit. And we could, if we wanted to, just declare a whole bunch of integers or declare a whole bunch of doubles and use them. But it might get complicated for us to try to figure out how this works. So if we look at our current capabilities, so let's say we wanted to administer the course COMP1511 in a C program. So we have combinations of different languages and stuff that we do all in the back end, like all your auto test code and all that kind of stuff. That's written in, I think we're going on 3 or 4 different languages that the back-end infrastructure for this course is running. But let's say, just as an example, I wanted to record everyone's marks in a program here. So I could do this with integers. So if we just look at what I've taught you so far, I'm going to need 1 integer for everyone's marks in this room. So, I don't know, we've got about 500 people in this room, so we would need 500 of these integers separately, and each person's mark is individual, so they're all going to need to be stored in memory separately. So I could do this like this. One of the annoying bits about this is if I want to test at the end of term who is passing the course, I need to see who's got a mark greater than or equal to 50. I can't even do this with a while loop. Because if I try to do this with a while loop, everything that's inside a while loop has to be the same code, right? Because it's going to repeat the same code over and over again. So I can't actually loop through and say, check the marks for student 1, and then the second time through the loop, check the marks for student 2. It's a different variable. It's in a different place in memory. I can't actually get the loop to look at different things. So what I might have to do in that case is write 500 if statements that are all identical, and ain't nobody got time for that. So we want a better way to do this. So we want a way that we could have, say, 500 of those integers and do a loop that just loops through 500 times and does the same code. I mean, that code would probably be as short as this entire example, and this example is only able to do 2 or 3 people. So this is where arrays come in. So an array is a collection of integers. What it is a series of integers that are all together in one group. And as a group, we can access them as if they're a single variable, but we can move through all the different integers and deal with them separately. So what an array actually is, a variable is a small amount of memory. So an integer variable is 32 bits worth of memory. A double variable is 64 bits worth of memory. And that's just exactly how much memory our computer gives us on our big long piece of tape. And it says, you got 32 of these squares for your integer. You can turn those into zeros and ones so that you can encode your integer any way you want. So usually we use something like a binary encoding for that. Don't worry too much about that. Although I think there was a tube question about that, so you can go deeper into it if you want to. I'm not going to cover that much in lectures, though. The array, then, is not just a single variable. It's the capability to hold multiple variables at once. So instead of just getting enough memory for one integer here, if I declare an array of integers, I get given enough memory for a whole bunch of them at once. So that means that when I declare this, it's like declaring a really, really big variable that's cut up into parts, and each part is the size of another variable. And so if I say I want an array of integers, this is cut up into 32-bit parts, and I get to see it as just one big chunk, and I can go through and look at each of those parts. So I'm going to create an array, and I'm going to give it a name in the same way that I would give another variable a name. But inside the array, each of the individual elements, each of the integers inside that array, they're not going to get their own name. So each of them is only going to be accessible via the name of the array itself, the variable that holds it. So some of the basic code that we might have for declaring an array, I can have an array of marks here. I should have spelled that with a C, and it would be all me. Anyway, so we have an array of marks, and it comes under this specific format. So up until this point, we haven't used the square bracket for anything, but as you've probably figured out at this point, programming loves different kinds of brackets, because we've had the normal brackets, we've had the curly braces, and now we have the square brackets. The square brackets are used for 2 different things. One thing they used when we declare an array to say what size it is. And then after we've declared the array, the square brackets continues to be the array's bracketing, and we'll use that to get certain elements out of the array. So for the moment, this array here, with its square brackets and 10, gives me, I go to my computer and I say, I would like a 10 integer array. So you can see that declaring it is really similar to declaring an integer variable. The only difference is the square brackets on the end. So I've declared this integer array called array of marks. And I have said I'm going to have 10 integers in this. I'm going to be given 320 bits worth of information separated into little 32-bit chunks that I can put separate integers into. This other bit on the end here is the initialization of the array, which is quite particular. So if we want to, we can try to initialize an entire array with this bottom line here, where I say, these are exactly the elements I want in the array. There's also, this is actually kind of a niche way of doing this. You won't always be doing this. But if we want to, if we just put a 0 in the curly brackets, it's just going to grab the whole array and make the whole array equal to 0. So it's going to take all the bits in the array and just turn them off. So all the numbers are going to start at 0, and then we can use them like that. So that's one way that we can initialize an array. It's also okay if you want to have an array that has no initialization, and you go through programmatically and put information into it. So we're going to look at a few of these things today, actually, because I want to code this up. I'm not going to hop into VLab and start coding just yet. I'm going to tell you a little bit more about it, and then we're going to go and start coding. So anyway, the declaration of the array is very similar to the declaration of a variable. You say its type, you say its name. The only difference is you then say how many of them you want in the array. I should point out another thing that's interesting about arrays is they're always connected together. So all of these integers are in one long line in our memory. So we don't have an integer here and another one over there and another one over there or anything. They're all in one big chunk. That won't be that important yet, but when we start using memory a lot deeper, you'll be able to see why that is useful. Okay. So the array has elements in it. So we refer to all the individual, for the moment, numbers, but we're going to have arrays of other things later. Every number in the array, every integer in the array is considered one element of the array. The way that we access the individual elements of the array is by what we call an index. And the index is just a number that says how far into the array do we need to go to find the particular number we're going to. So it's always going to start at 0. And 0 says, I want the first element of the array. So 0 says, I'm not moving into the array at all. I'm just reading from the very beginning of the array. And then if I go into higher numbers, it's like, take this many steps into the array and then read the number that's there. So it can be a little weird the first time we look at things like this to be like, why are we counting from 0? But the reason we're counting from 0 is in a way, we're counting programmatically now. So to look at the first thing in the array, we don't say 1, because 1 would imply we're moving one step. So since we're not moving one step, we're reading the first thing in the array. And then if we're reading this element of the array, we're there, we have to step 3 times to get to that element of the array. So every time we're going to use something in the array, when we're looking for an individual element of the array, we're going to use its index number to find it. And I'll show you the code for how we do that. This can be a point of confusion for a lot of people the first time you work with these. The square brackets have 2 different functions. I shouldn't use the word function. Function is something else. They have 2 different uses. When we create the array, the square bracket says how big it's going to be. So it says how much memory we need and how many of these variables we're going to put in it. After it's created, we can then use it. So we could use it in the same way we can use other variables by using its name. But the thing about it is there's not much we can do with the array as a whole, because the array as a whole is a whole series of numbers, and so we can't do any maths on the whole array. If we want to do some maths with it, we need to do individual elements. So we need to pick out a specific element. So here we can see I want to set the first element to 85. So if I say array of marks and 0, so this is not me declaring a 0-length array. This is after it's been made. I can then use it by saying its name, putting the square brackets after it, and putting a number in there. This is going to be an integer because we can't get halfway between elements in an array. This gives me access to the first element of the array. So if I go back to my diagram here, me saying array of marks square bracket 0 says I'm looking at this number. So I've gone into my memory, I've gone to the start of the array and said I'm not stepping into the array because it's a 0, I'm looking at the first thing in the array. So that's currently a 55. But this piece of code here says this thing, array of marks 0, it's an integer. Because I've said here, since I built them as integers, and I say I'm looking at the first integer there by saying 0. If I say equals 85, that means I'm writing an 85 into that. So if I'm like walking along my piece of tape in my cardboard box, I'm like, okay, go to the start of that array, somewhere on the tape, find the first element of that, which means we go to the start of the array, we don't go any further with a 0, and rub out whatever's written there and write an 85 in there instead. We can access the index of an array using a variable's value as well. So if I have a variable here and I set it to the value 3, I can then do array of marks using the access index. And this will give me the fourth variable in the array because it starts at the first one, it steps in 3 times. So this way I can access parts of the array using a variable or access parts of the array using just a raw number. This means that if I want to, I can work my way through an array using a variable that changes, and then that variable that changes allows me to access different parts of the array. We can even do cool things like this. So anytime I get an array and I put the square brackets afterwards, put a number in that, that's me accessing one of the integers in the array. I can treat that exactly like I would treat a normal integer, and I could do any of the code we've been doing previously on integers with an element of an array. So I can get one element of the array and copy it over another element of the array. This is the same as me saying x equals 5 or something like that, right? This is me saying the this is the third element of the array will be overwritten by the 7th element of the array. So you just read the value from this one and you write it into this memory location in the same way that we could read a value like 50 and write it into a variable somewhere else. There are issues that we can have, and this is one of the most common ones, is trying to access an element that doesn't exist in the array. So if I say array of marks 10, what's going to happen is I start at the first element of the array and I skip in. Let me go back to the diagram of the array. If I'm here in the array and I skip forward from 0 10 times, 9 is here, 10 is here. So if I skipped in 10 times, I would end up off the end of the array. So if I try to index something past how many elements it has, so it's a size 10, the first one is 0, the last one is 9. If I go to index 10, what I'm going to end up doing is trying to go off the end of the array, which means my little person in their cardboard box has walked to the end of the memory that they had for the array, and then they've walked past it, and they've tried to write stuff on the paper there, which means they're trying to write to memory that they didn't actually have. So they didn't have it set up for writing an integer, and they tried to write to it. That's going to cause problems. Your computer will most likely throw an error in this case. There are older systems, and some of you may or may not be setting up your own systems on your laptops to use. Some of those don't have the same kind of error checking that we've put into DCC. They may allow you to do that, and then you're going to end up potentially writing into pieces of memory that is overriding other variables. So all the variables, if I go back to this slide, were together in this space here. If you've got an array and you've got some variables afterwards, you could potentially walk off the end of the array and then write into other parts of your program. Little bit of trivia there, that's one of the oldest ways to hack a computer. So if you could get access to memory that was near in your RAM to the program that was doing password checking, and you ran off the end of an array in your program and kept going into the other program, you could actually write different instructions into other parts of the code. So anyone wants to get into cybersecurity, that kind of thing, this is like, I don't even know if this works anymore. I'm pretty sure it doesn't work because it's so easy to do. But that's actually one of the oldest ways to hack a computer, is to get a program running on the computer, run off the memory from that into some other program's memory, rewrite things in there, and then the next time that thing runs, it's running for you. So old school. Again, that's another one of those things where, yeah, you can spend a few years just from that statement and the ramifications of where that goes. Okay. When we're using arrays, we have some other things that we need to think about. So when we're using arrays, we can't printf a whole array, and neither can we scanf a whole array. So all we can do is go through and look at the individual elements of the array, and we look at those individual elements, we can printf and scanf them, because as I was saying, the individual elements act just like integers, and so we can use them just like integers. So instead of trying to printf a whole array and have all the numbers come out one by one, we're going to have to do that ourselves. So we're going to do that by using something like a while loop, and the loop is going to be able to go through all of the elements of the array and then grab them one by one and do something with them. You'll see how this, in a second when I do it, you'll see how one of the while loops I've been showing you fits together absolutely perfectly with arrays. But I'll show you in a second. So if we wanted to scanf or printf, we can do this kind of thing where we treat one of the elements in the array as an integer, and then we can do exactly the same things we do with scanf and printf. So the fifth element of the array is going to be at the index number 4, because the first element's at 0, 1, 2, 3, 4, gives me my fifth element. However, we cannot do this. So we can't say, let me scanf 10, is it 10? Yeah, let me scanf 10 integers, please write all 10 integers into the array. Unfortunately, C is not quite, I don't know, expressive enough as a programming language to be able to do that, so we would do that kind of thing ourselves. Oh, I don't have a slide for it. Oh no, I don't have a slide for it because we're going to do it. So let's go to break now. And I've got a little XKCD comic here. This kind of follows on from yesterday about what we're trying to do with coding. And hopefully, I think this is going to resonate with a lot of people. This is what professional coders feel like about code as well. So we'll take 5 minutes, and then we're going to launch into it, and we're actually going to build a program. We're going to use some arrays, possibly some functions, and learn a bit more about how this all works.
Hey, Matt. Hiya.
Hey, how's it going?
Good, thanks. I want to clarify, is the heap data structure that you showed, is it the same as a binary tree diagram? Is that
it's not.
Oh, so it's different.
But it's named the same. I think that a lot of the time they are organized the same way.
So like a tree diagram?
Yeah, so it's organized in memory similar to that.
Oh, okay.
But I don't know actually, because I don't usually go down to that level. I treat it as a bunch of memory that I can use. But I don't know exactly if it's organized in that data structure or not.
Oh, okay.
Yeah.
I looked at heap and stack before.
Yeah.
And there were data structures, but in this case.
Yeah, the stack is that. The stack is you pile stuff on top of each other, and you can only use the thing on the top. Yeah, yeah. I'm going to assume the heap is, but I don't go down to that level of programming usually. Yeah.
By the way.
Yeah.
Let me clarify. You cannot change the size of the array, correct?
No, you can't.
It's non-modifiable.
Yeah.
Okay, cool.
So it's not a vector. If you've done other programming, yeah.
Yeah, I did Python.
Yeah, Python has vectors, right?
Yeah,
yeah.
I think it does, yeah.
Yeah. Well, C++ definitely has vectors. What those things do is when you go off the end of the array, they will grab the whole thing, find another piece of memory that's bigger, and rewrite it in there with enough space to grow. Yeah. But our arrays are fixed. They don't move around.
By the way, what happens if you don't initialize, if you do not initialize an array? Let's say you leave it blank. Do you get an error?
You get the same thing you do if you don't initialize an integer.
Okay.
They're going to be weird values that don't make any sense. Depending on your compiler, it's going to be different as well. So this is what we call undefined behavior. Where you don't know what it's going to be. So if you declared an array and read from it, it would depend on your compiler. Some compilers give you zeros. Some compilers give you the magic integer number. Other compilers give you whatever was in memory. So they don't even overwrite what was there. You can just read whatever was there. And so it's messy. It's really messy if you don't initialize.
Saying that, because I want to accustom myself to DCC. Is there a way to install DCC? I've found that with GCC,
it doesn't give you errors, right? Yeah, it lets you do really dangerous things. So there is a GitHub for DCC where you can download it, and it runs, I think, mostly in Python. I haven't tried installing it on a Windows machine, but I think it works.
I've got Linux here.
Oh, if you're running Linux, it'll totally
I
work.
just have
Yeah.
one quick question.
Yeah, hey.
Are we going to be tested on the programming? Are we going to be tested on the CPU and RAM stuff?
Not really. Only a little bit. Yeah, I don't think so.
So it's only going to be pure programming in the front.
Yeah.
There are theoretical questions as well, but they won't necessarily be on this other stuff. So when I'm introducing a concept to you as a cool idea for things that you could do in the future or things that are going to help your understanding, it's less likely to be examined, but I'll examine your understanding of it.
It'll be like a sample test before the test, right?
No. The weekly tests are...
There's nothing about computer hardware or RAM.
Yeah. So that's mostly trivia. Yeah. Cool. All right, I better get going again.
Let's go.
Yep. Okay, let's get started again. All right, everybody, if I could have your attention. Is this thing loud enough? Maybe I need to yell louder. Hello? Okay. All right, everyone, settle, let's go. Okay. Let us continue. Because I've now talked for 3 hours worth of lecture, so that was 2 hours yesterday and 1 hour today. Sorry, I didn't mean that right now. We haven't gone through a time warp and magically gotten 3 hours. I would love to be able to talk for longer, but I physically can't do it that well anyway. But I've just done 3 hours worth of lecturing, so 2 hours yesterday and 1 hour today, without necessarily building any code to teach us about what we're doing. So I'm going to spend the rest of this lecture doing some code that will hopefully teach you a lot about using arrays, combining arrays with looping, and also I'm going to throw in at least one function in there as well so you can see a function in use. So I would like to write a program using arrays that tracks scores in a game. So the example I used previously was marks in a course, but that's a little bit too close to home, so I'm going to keep the example something light so that if someone loses in this example, it's not the same as having failed a course or something like that. It's really not that big a deal, by the way. People fail courses all the time. It's fine. So in this game, we've got 4 players playing in the game, and we want to be able to set their scores to different amounts, which means I'm going to need a different integer for each player. We also want to be able to tell at any point in time who is winning and who is losing in the game, and we want to know maybe how many points have been scored in total. So I don't know if I'm going to stick exactly to this, but I'm going to do something like this. But basically what we're going to have is we're going to try to build up an array of scores and look at different ways that we can access this array. How do we loop through this array? How do we check for different things in it? So this is going to be the same thing that we're going to talk about every time we have a question about what we're going to do. So we're going to start off with the idea that we need to build something. And when we talk about needing to build something, we can see the finished product in our mind. Seeing the finished product in your mind is useful because that keeps you on track to aim towards the finished product, but it's not actually that useful in terms of what are we going to start building. So one of the hardest things is to say, okay, what do I start building if that's the finished product? Because the finished product is all the way over there, and I'm here and I need to build all the pieces to get there. So the first thing that we need to do is think about what does this program need? So one of the things that we can probably agree that this program is going to need is it's going to need an array of numbers because we're storing scores. We don't necessarily know whether that array of numbers is an integer array or a double array because we don't know how the scoring works in this particular game. But we're just going to probably make those decisions because we don't actually have that information. I'm just going to make that up as I go. But if we are going to store multiple people's scores, then we're going to need to create an array. In order to access the individual people's scores, we're going to need an index that's able to change its value to move into different parts of the array. If we are going to look through all of the values in the array, then we're going to need while loops to move through that. So this is me in a sense. So I've got my virtual toolbox, and I open my virtual toolbox, and in my virtual toolbox I've got all the things I've learned. So in there's arrays, there's functions, there's while loops and things like that, and I'm getting those out one by one and saying, okay, which of these am I going to use to build this thing? And I think that most of what I'm going to be doing is grabbing my little while loop thing and saying I'm going to apply this while loop to this array multiple times in different ways to get different information out of it. So let's start putting this together. We're going to do something really simple first. And we're going to set up an array, and then we're just going to put numbers into it. But then what we might do is we might look at what happens when we try to output all of the information from the array. So I'm going to hop out of the slides mostly now and into my VLab here. I'm going to my COMP1511 directory. Have I made? I haven't made a lecture 6 yet. Oops, not CD. I need to make the directory first. Okay. CD to lecture 6. Now that I'm in my lecture 6 directory, I'm going to make the code file that I'm going to use by opening my editor. What was it called? I'm not sure. So it's something that tracks player scores. So I'm going to call it player scores. And allows me to run the editor and the terminal in parallel. Okay. So I have here my code file. I'm going to stretch it there so I can see everything. Has nothing in it yet. So the first thing I'm going to do is set up the same way I'm going to set up any C program. So I'm going to say a program that tracks players' scores in a game. This is also a demo of arrays. Oops. It auto-completed arrays to game. I don't know why I did that. It was made by me. Wow, we're in March. That's a bit scary. Okay, some of the things I'm going to need for this. I'm going to do my most standard setup by including my input-output standard library so that I can work with Printf and Scanf and stuff so that I can just see stuff happening. I'm going to need a main. Now, we were looking at functions yesterday and understanding that this is a function, the main function. The void keyword here says that there's not going to be any input into this. We don't actually use the void keyword that often when we're programming our own functions. If anything, we would use a void keyword for the output of the function, but not necessarily for the input. The main's a little bit different, so that's why it has a void there. Okay, I put my return 0. This is a good point to start, because at this point, I could compile this program, and it would compile successfully, and it would be able to run. Well, assuming I haven't made a typo somewhere there, but I'm expecting this will probably compile and run. It won't do anything, but this is my framework so that I can start building stuff inside it. So some of the things that I said I was going to do was I was going to create an array for the player's scores. So I could call it scores, and I could say it has 4 elements. So this is the most basic possible form of this that I could do. One thing, though, that I might want to do, and you can see this because it was on the slides, so I've already spoiled this before I started writing, is what if the game isn't always going to have 4 players in it? What if someone can't make it that day to play, and I want to switch this to use 3 players or something? Or what if someone makes a whole new game, and in the DLC expansion that you can buy for this game, you can add 5 or 6 players to this game, and so I want this to be able to change and not be locked into 4 players. I might define the number of players for now to be 4, but in the future for me to be able to change it easily to something else. So I can say num players here. I have a choice now whether I want to initialize this thing or not. So if I want to initialize it with zeros, I can say all players start off with 0 by doing the following. This is a special case, by the way. This only works with zeros. So we can't try to start everyone off at 100. The zero is a really special case. However, there are other things we could do. If we wanted to set it up in a different way, what I could do immediately is I could write a while loop that sets up my players by going through this array individually and setting them up to different things. But before we start getting into looping, let's just get into the basics of what we're doing. So as we were doing on the slide here, I just wanted to show you, I've let another variable go in there, so there could be a counter for me to loop, but we'll leave that out for now. If I wanted to just explicitly go in and say, okay, this player has this score, this player has this score, etc., I can do that by accessing the individual indexes in this scores array. One thing I should say about naming for arrays, I have a bit of advice for naming. So variables are nouns, functions, which we haven't made any yet, but we will soon, are going to be verbs. When we do arrays of variables, the best thing to do is to give them a plural noun. So a plural noun means it's the name for a group of objects. So scores is good. If I called this score, it still is implying the purpose of the array, but we're going to really easily get this confused with an individual integer if we use it again later. So I prefer, if we're making an array, to make it sound like there are multiple things in it, and it makes it just easier for us to think about things as we go along. So little things like that will help you name your variables later, and they'll hopefully help you in your error checking when you're looking through your variables trying to figure out if they do the right thing or not. Okay, so the first time I use the square brackets with an array, when I'm creating the array, that is going to decide how big the array is. From then on, every time I use the square brackets in the array, this is not going to have anything to do, well, it has a little bit, but not that much to do with the size of the array. This is me looking for an individual part of the array. So if I do scores 0, that's me saying the first element of the array. So I go to the start of the array and I don't step into the array at all, so 0. This is me getting to the first integer in scores. Let me just open up Paint here. So, me creating an array with 4 elements in it does this. So I'm going to call this thing scores. Is that working okay? Yeah, cool. This is a new thing. I just got a laptop that has a stylus, and so this means I can play around with this. So if I was to write the indexes for this, let me pick a different color. I'll try to make these colors really bright and contrasting in case anyone's colorblind. Okay, so 0, 1, 1, 2, and 3. So those are the index. I'm an artist, I swear. I actually do a lot of painting in my spare time, so this is shameful. So 0, 1, 2, and 3 are the indexes with which I would be grabbing those values or accessing those integers that are inside those little boxes there that I've created. So if I come back here to my code, scores 0 gives me access to the first element there, and I want to set that up as a particular number. So let's just say for the moment we're going to use scores between 0 and 100. Someone give me a score for the first player. 2? I heard a 2. Hopefully. I don't know if someone actually said 2 or not. So But thank you for giving me a one-digit number, because it means it's less likely for me to get this wrong here. So I'll use red. What that does is it puts a 2 in there. So that has gone to the 0 element. Oops. The 0 element, which is the first thing there, and puts a 2 in. If I was to go through now and put in other numbers for other people's scores, anyone want to yell out some numbers at me? 21. 6 and 21. Oops. Oh, hey, what happens if I do this? It's not going to work. So we're probably going to get an error here because the array itself is not big enough to get to 21. So that was me just having a little brain fart and typing in exactly the number that someone had just yelled at me. Did we have another? Wait, someone said 400, but we were only going to go up to 100, so I'm going to do the classic integers. I'm just going to truncate it. It ended up 40. I just ignored your final digit. Okay. So doing this means the number in the brackets, the number in the square brackets is me choosing which integer in the list of 4 that I'm going to go to. So the second one, score 1, here was 6. Scores 2 was 21. And I'm going to wish that I drew these bigger. And the third one was 40. Okay, so this is what my memory is going to look like after I've executed these commands. So I made an array, and it was exactly size 4. This is slightly dangerous, though. This code I've written here is slightly dangerous because what if I changed num players to 3 and then tried to run that code again? I would have a problem. So this is just sort of an example of what we can do to access elements, but once we get deeper into it, we probably won't be doing this explicitly like this with these exact numbers. But anyway, each of these scores, square brackets something, is giving us access to an individual integer that is part of that array. So that's why they all have the same variable name at the beginning, but the index, the number going into the square brackets, allows me to access different parts of it. So with this here, going in like this, we've hit a certain point where we know that our array has been populated with values, but if we run this program, we don't really have any way of figuring out whether this worked or not. So what I might do, I've gone off the slides now, I'm not sure if I'm actually up to this yet. Oh, yep, no, good. I did write the slides, so hopefully they go on the same idea of what I want to do. In order to see whether this works or not, I need to be able to display what's happening. So maybe what I want to do is have some code that is going to print out all of these numbers to the terminal so I can see whether my putting the numbers in has worked or not. Or later on, if I change the numbers, I want to be able to print this out. So I want to print out the 4 values for the scores that are currently in the game. And I'm thinking already at this point that this is something I'm going to want to do more than once. So as I make changes to the game, as I do things, I'm probably going to want to print out the scores multiple times. So if I want to be able to run this code multiple times, I'm probably going to put it in a function so that I don't have to write the code again and again and again, the while loop again and again and again to print out the scores. What I can do is I can put that separately somewhere else, and I can say, okay, run that code again. So I'm going to make a function here that displays the current scores. So I'm going to call it display scores. If you remember from the end yesterday, I was showing how in order to create a function, first we need to let the main know that the function exists. This function is going to print stuff to the screen using something like a printf, but I don't think I need to get any information back from it into the program. So it's going to be a void function. Display scores. I'm calling it display scores because I think that makes sense for me. That's roughly what it's going to be doing. When I create a function, I need to know what information needs to go into that function. So let me start writing the function itself. I'm going to just put some white space down there so I'm working in the middle of the screen for you to see. Print all current scores to the terminal. And this is going to be the same as this up here. So I'm going to call it void. I'll use my autocomplete there, display scores. Open and close my brackets, so I have a function here. Question then? Oh, the question was, is there a difference if I define the function above or below the main? So, for example, if I was to take this one out, so comment it out so that the computer can't read it, this will definitely cause an issue, because if I was to do something like this, I say run display scores, it wouldn't be able to run display scores because it doesn't know what it is, because there was nothing above it. The other idea is, what if I take this and I put that up there, so I won't need this, and I can put this up here instead. So I can put the whole function before the main, so the program knows entirely what display scores does before the main runs. This will work. So this is okay because it allows us to see exactly what display scores is going to be before the main is going to use it. The downside to this is the more of these and extra lines of code we put in here, the further away the main gets from the start of the file. The problem with this is a human problem, because what a human needs to see first is the main. Because you want to see, where does the program start, what happens in the main idea of the program itself, and the further away we push that from the start of the file, the more annoying it is to find it and read it. So the reason why we do this declare one line above and then multiple lines below is so the first big chunk of code that we read in our programs is always going to be the main, and then we see what's going on for the core idea of the program without getting confused by these other side program bits that we've created. So that's why we're always going to do it in this kind of layout. Okay, so I'm creating a function here. And functions follow the same kind of rules that I have given you before about curly brackets. What goes on inside the curly brackets stays inside the curly brackets. I always laugh when I say that. It's just too funny. So if I try to do something like this, printf, I'm just going to do something really simple, %d scores 0. Given that I have given you a clue about the curly brackets, does anyone have any idea what's going to happen if I try to run this? That's someone up the back there? Yep. Say again, sorry? Yes, exactly. So the answer there was, there is no such thing as scores. Because this scores exists between here and here. This is a different set of curly brackets. It does not know what scores is. And this is why we give information to our functions. So what I can do is I can say one of the inputs to this is an array of scores. I'm actually going to name this differently here so that you can see the difference between them, because they're not exactly the same. This is going to be an array of size num players. One of the nice things about having that hash define, a hash define is outside of all of the curly brackets, so it actually carries through our entire program like that. So I can do this like this. And for this to be the same function as this one here, its first line has to be identical. So I'm going to need this part. Down here. So what I'm then going to get is when I pass scores into the function display scores. So this is kind of a demo of how these functions work. So I've created an array called scores here, and I have a function that when it runs, it wants to have an array of scores given to it, and I give it, well, it's not an array of scores, it's an array of integers given to it. I give it the right kind of array of integers, because you can see the declaration of this is the same as this. It's an array of integers of size num players, and so I can put scores in here. Note that I didn't put any square brackets on the end of this. If I was to put square brackets on the end of this, let's say I put a 3 in there, I am no longer passing an array to this function. I am passing one of the integers in the array to this function. So if it wants the whole array, I give it the whole array, which is just the name of the variable. Question there?
So was it necessary to define the size of the array?
The question was, is it necessary to define the size of the array in the function there? It's not necessarily. You can actually do this by saying there's some kind of array. But I was kind of doing that as a guarantee to make sure that I'm getting the right array in. I think that it might work either way. This is one of those funny things where I've got into a habit of doing it like the safest possible way, and I don't know how unsafe we can be here and still survive. So let's try it without. I'm pretty sure this is still going to compile. If it throws errors, then I'll look into it and we'll see what we can do. So I'm going to assume that the array I've been given is an array that is num players size, so I'm going to work with it as if it's like that. Okay, there's still no scores, but there is score array, because this variable here, all of the variables that are in our input, the input parameters of our function, are going to be available to us inside the function. It's not exactly that those variables are available. Usually those variables are recreated inside the function. I'll go into more detail on that later. So if I want to go through and print out all of the scores in the array, I can do this if I want to. So print off this. And there's 1, 2, and 3. But as you're probably guessing here, this is not a nice way of doing this, and this isn't robust in any way to us changing the number of players. So instead of repeating code like this, I don't like repeating code, I don't like having to copy paste stuff, I'm going to loop through this instead. So I'm actually going to ditch this whole thing. And I'm going to say, let's loop through all the scores, and looping through all of them, we're going to print them out one at a time. So I'm going to start off with a counter. I'm going to call mine I. You know how I was talking yesterday about, well, not yesterday, was it last week, about iterators, that sometimes we call them I. And then I'm going to do a while loop that goes through the array. This is going to be one of my standard while loops. You know how I was doing while loops? We say I want to run an exact number of times. So I set up a number starting at 0. This is also, now you can tell why I started it at 0, because I was making these specifically to go through arrays, and the arrays also start at 0. So while I is less than the number of players, so that's the number of times I want this thing to run, and I'm going to do my I++ that increases I after each time I go through the loop. So this code should look at least a little bit familiar. I mean, apart from me putting the num players in there, this should be reasonably familiar in that this is a while loop that I know I've set up specifically that will run an exact number of times. And that number of times is num players. Every time this while loop runs, I will be equal to a certain thing. I can put a comment in here saying, have processed I number of players. So every time I go through this loop, I is going to be equal to a certain thing. So when it starts at 0, I know I've processed 0 players, and then as I go through, I will know how many I have. And when I exit the loop, I know that I is now equal to num players. Because I know it went up by 1 each time, and then the second it reaches num players, that's what it's going to be equal to. So little comments like that allow me to just go, okay, this is exactly what my loop is doing. So if I've processed that number of players, I need to process that particular player at that time. So when I is equal to something, that allows me access to something inside this array. So I can access this particular variable, score array I. I mean, this code doesn't do anything yet, but I just want to show you me accessing this. If I go for the integer score array I, the first time I go through the loop, I get the first integer. Second time I go through the loop, I get the second integer. Third's the third, fourth's the fourth, that kind of thing. So my counter here, my counter variable, which is currently I, is not just counting how many times I'm going through the loop. It's actually like a marker. Oops. Did I press the button? That starts here and then says, okay, second time through the loop, I then end up here. Actually, I'm just going to keep drawing these. And then I end up here. And then I end up here. So your I now is not just a number counting how many times you're going through the loop. It is also an index into the array that moves along the array and allows you to loop through the array, grabbing each element at a time and doing something with it. Okay, so this will get me each element in the array once at a time as we go through the loop. So what I'm going to do is I'm going to do a printf. And what should I say? Player someone's score is something. Actually, I probably don't even need the full stop there. And then I'll put an end line on the end, so this is going to print one player per row. So the first thing is the player number, and that's going to be I. So that might be a little bit confusing because we're going to have players 0, 1, 2, and 3, but that's okay. I'm going to leave that like that for the moment. Or if I wanted to, I could say I plus 1. Oops, forgot my spaces. And then it would be players 1, 2, 3, and 4. But I might just leave it 0, 1, 2, and 3 while we're doing this demo, so we're thinking about the indexes into the array. And then we say what their score is, which is this thing here, which I've just made. I'm just going to delete that because I don't need that there. Oops, I paged up. So the second value that I'm going to print out is the actual integer in the array. So score array, spell that correctly. And I is the index into the array. So I'm saying this is the index I'm looking at, and this is the value in that index. So when we run this now, we're going to get, this is going to create the array, this is going to populate the array with numbers. This function, when my main hits here, it's going to jump over to here, and it's going to say, okay, I've been given an array, then I will use that, and I will loop through that array and print out the scores. So hopefully if I compile and run this now, I'm going to get a program that prints out each of these 4 players' scores. So let's check that. I'm just going to clear that. So I'm going to DCC to compile that. What was it called? Player scores. We're just going to call my program scores, so it's quicker for me to type in. /scores to run that. So one point that we know from the question earlier is that I can create a function with an array with no fixed size, and that's at least going to accept that that's correct C syntax. Whether it runs what we want it to, we'll find out in a second. Okay, so /scores is going to run my program. Cool. So we can see that this is all working for the moment. we can pass the score array into display scores, and display scores is now capable of running. And if I want to, this is one of the beauty of using functions, I can run a function more than once. I mean, this is not going to give us any new information. But instead of writing that while loop out multiple times, I can now just call the function's name multiple times, and it will be able to run multiple times. So if I compile that, I'll make sure I saved it. Compile that and run that. It's now printing out the scores twice. Right? So that function is now something that I can use anytime I want it to. Okay. So we can loop through and see the values. Oh, I've got a whole lot of... Right. Okay, now that we know how to loop through that array, we can do some of the things that were getting some interesting stats out of this array. So what we could do if we want to now is we can loop through the whole array and we can say, can we find the highest value in the array, the lowest value in the array? So can we find out who's winning or who's losing at this point in time? Or can we find out what the total is of everyone's scores? So what I'm going to do, I'm just going to leave that as it is, and I'm going to add some other stuff here. So the stuff I'm going to put in here, I'm going to write some of it in the main, but some of it could definitely be pushed into other functions. So if I wanted to, I could have something like another function that says display winner, another function that says display loser, and they would also be in their own functions. But for the moment, what I'm going to do is just show you how I'm going to loop through the scores itself. Or actually, if I'm going to combine them all into one loop, then it might be better if I put them all in the main. Either way, I want to loop through everything in my... I should not try to write code and speak at the same time. So I'm going to try to loop through all the scores in the array, and I'm going to try to grab some information from them. So the first thing I'm going to do is just build up the structure of the code, so the looping that's going to go through everything. So while this is going to be the same loop, actually, as the one that I used in display scores, because it's going to do the same thing. It's going through everything in the list and looking at each one at a time. So I like to build up my structure like this to begin with. So my while loop structure there is solid. I haven't left anything out. This is going to run exactly a certain number of times, and I know that it's going to stop. So this is the thing that I think I was saying previously, is every time you create a loop, figure out how it's going to stop, and then go in and figure out what code goes inside it. Because if I forget how it's going to stop, I could do something like forget to put something in there, and then this loop goes forever. If it even runs, I'm not sure if it runs if we don't put anything in the question in the while loop. Or I do something like this. This loop will also go forever. Because if I don't change the value of I, and I starts off less than num players, then it's going to stay less than num players forever. Question there.
So for counting loops, why don't you use the
Oh, the question was, for loops like this where we're counting stuff, why don't we use a for loop? The reason's basically that the while loop can do anything the for loop can. I mean, if you know for loops, you can use them to a certain extent. But the reason why we're not using for loops here is they do things in a weird order. So if we're learning coding, like I assume you know for loops already, right? So if I'm learning coding for the first time, it's really easy to read a while loop because it does everything line by line in order. And also it can do everything a for loop can. So that's why. All right. So if I do this, having said that, I do agree that sometimes with for loops, it's easier to not forget parts of it. Yeah. So with the while loop here, this will go through exactly a certain number of times, depending on num players. It'll go through num players number of times. And each time it goes through, I will be equal to one of the indexes in the array. So let's think about what information that we want to get out of this. So this is, again, that idea that I was talking about previously about writing the comments first and then writing the code, because then it's easier to think about what you're going to do. So loop through and find the current winner, highest score. Okay, so if we want to loop through and find the highest score, what we need to do is to keep track of something as we're going through the loop. So this is some of the stuff that we're going to be doing with looping, which is like the most fundamental things. So one of them is be able to loop through the entire list. I shouldn't call it a list. List is a keyword for other things. Loop through the entire array and do the same thing to everything in the array. I am going to loop through the entire array and do the same thing to everything in the array. But what I also want to do is I want to track some information. So what I want to do is I want to track what the highest score is. And then if I go through everything in the array and compare them all against the highest score, I will know which one is the highest. I'll show you how this works. So, following the rule of what goes on inside the curly braces stays inside the curly braces. Any variables that I create inside the while loop, they last for exactly one iteration. So they won't last longer than one loop through. So if I want something to last longer than one loop through, it has to be outside the while loop. So I'm going to have an integer that tracks the highest score. So if I have an integer that tracks the highest score, what I'm going to do first is a little trick. I'm going to set it to -1. So I'm assuming for the moment that those scores are between 0 and 100. So I might want to say that. Assuming scores are greater than 0. And then what I'm going to do is I'm going to go through. Where are we? My paint here. I'm going to go through this list. And so I've got highest, which is, oops. Thought I changed it. This is my highest somewhere else, and that's going to start off as a -1. And then as I go through my list of scores, I'm going to compare them against the highest. And if any of those scores are higher than the highest, they're going to replace what I can see as the highest. So highest is not a fixed value, it's a variable, and it's going to change as I go through the array. So for example, if I start going through this array, and I look at the 2 first. I look at the 2, and the 2 is higher than -1. So since the 2 is higher than -1, the 2 is going to replace the -1 as the current highest, because it will be the highest that I've seen. 2 there. And then I'm going to keep looping through, and I'm going to get to the 6. So when I get to the 6, I compare the 6 against the 2, and I say, which of you is higher? 6 is higher, so 6 is now the highest that I've seen so far. I'm going to keep going along. 21 is going to be higher than 6. So 21 would go in there. And then I'm going to go again, and the 40 is going to be high. I'm not going to bother writing the 21 because I know the 40 is just about to replace it. The 40 is higher than the 21 as well. So the 40 is going to become the highest. And now I've tracked, because I know I've gone through and I've looked at everything in the list, I know that whatever I have in the highest at the end is the highest score. The other thing I might want to do here, because this is a game where I'm reporting who is winning, I don't just want to know what the highest is. I also want to track the index of the highest. So I might call that index highest. And so what this is going to do is every time I replace the highest score, it's going to tell me which player was the highest score. At the end of that, I should be able to print out who's winning the game. So this would be index 3 by the end. So let's look at that in code. So I have my highest that starts at -1. And I called it index highest, I think. I don't really have a good option for what this should be at the beginning. But I could also make this -1 just to say, if this remains -1 at the end of my loop, then I know that something's gone wrong. So, inside my while loop, I need to do some checking. And the checking I was going to do was to compare the current highest. I actually could call this current highest. Might make it easier to understand. Current highest. So I'm checking the current highest against the number I'm looking at in the loop, because I'm going to go through the loop and look at the actual scores in there. So if I'm checking something against something, the implication there is I'm going to use an if statement. And I'm going to check, is the current number I'm looking at, which is scores I, because this while loop is going through the array scores and picking things up. So if scores I is greater than the current highest, then what I'm going to do is I'm going to say I is the highest scoring player. So if this if statement triggers, it means that whatever score was in I was higher than the previous highest that I'd seen as I was going through the list. So if I is the highest scoring player, then I know that the index of the highest is now going to be set to the index of the highest scoring player, which is I. And I'm also going to track the highest score so that if I go through later and I find someone else with the highest score, this is what I'm going to compare it against. So the current highest, if I wanted to be really pedantic, I would be saying that's current highest score, but I don't want my variable names to be just like, forever long. So current highest will do, is equal to the score of this player. So the score of this player is the integer in the array of scores that this player has earned. So this is me using a loop, using I to be the iterator that moves through the array of things and attracts which number it's looking at and which player it's looking at. And if that player's score is the highest score that we've seen so far, it replaces the highest score we've seen so far with its own score, and we track whose score it was with the I. So as I go through my list of scores, I'm going to be able to update who's the highest player until the while loop ends. And when the while loop ends, I know a few things for certain. I know that I've looked at every single score in the game, and I've compared every single score against the highest that I've seen so far. And so the only thing left in these variables should be the index of whoever has the highest score, as well as what score they have at that point in time. So knowing that, I could then print out player something is currently winning with a score of something. So which player is it? It's the index of the highest. So this is whatever index of player was the one who'd won, or who had gone through this while loop and ended up on top. Note that these variables are outside the while loop, so they don't get destroyed when the while loop finishes. The only things that get destroyed in the while loop finishes is anything I create in here, which means these things persist longer than the while loop, which means I can use them in my print statement that happens after the while loop. So the player currently winning is, oops, that doesn't go in there. I'm going to put this on another line, make it easier for myself. Is index highest. I'm going to auto-complete that. So the first number is the index of the person who's winning, and the second is their score, which is the current highest score. Okay. So this code here should, as it goes through the loop, track who's winning at this point, and when they are winning, they'll be able to print out who they are and how much their score is. Yeah, we've got a question there.
If your player won, your index would be 0 and output player 0.
Yeah. Yeah, so the question here was like, we have a player 0 still because if we have index 0, it's going to say player 0. We saw that a second ago with the display scores as well. I was thinking about making it players 1, 2, 3, and 4, but what we're going to do is we're going to keep players 0, 1, 2, and 3, just because we're in the context here that we're learning about arrays. So I want to keep them as indexes so that we can just remember that it's going to be 0 at the start of the index for all the arrays that we're going to use. Okay, let's run this and see if it gives us the information we're looking for. I'll make sure I save it first. Control S there. I'm going to compile this. I should be able to use my up arrow to find my previous compilation. And then I'm going to run it again with /scores. So hopefully we're okay with the 0 through to 3. Player 0 score is 2, 1 is 6, etc. And then player 3 is currently winning with a score of 40. So now we have a situation where we can go through and we can find the highest score. If I was to go back here and make some changes, so I just want to prove to you that this thing can track the highest score no matter where it is in the array. It's not just going to the end of the array and finding the highest. If it finds the highest early, then it won't replace the highest with any of the things that are lower than it, because this if statement will only trigger if the score it sees in the array is higher than the highest thing it's seen so far. So let's go through now with a different set of scores and see if this thing is still tracking the highest. By the way, this is the kind of thing that we would do when we're writing the auto tests for stuff like your labs. We will say, okay, what are the different situations this program must be able to react to? And we'll put a few different examples in there. The other thing we could do here is not explicitly type in the scores, but we could run a while loop of scanfs and enter information into the program. Actually, yeah, 10 minutes. Should I do that? Let's do that. Okay. I am going to, instead of changing this like this, actually let me just run this once at least so you can see whether this highest score tracker thing is actually working or not. All right, I'm going to save this, going to compile it, and run it. Cool. All right, so 2, 65, 1, and 40. This is giving me at least a little bit of information, not entirely proving it, but a little information that says that the thing that's tracking the high scores is able to find a high score not only at the end of the list, but partway through the list as well. Okay. In order to make this more dynamic, I'm going to change this code here from something we'd have to recompile each time to being able to actually take input from the user for the scores. So I'm going to call this one counter, or maybe I'll call it input counter. And this is also going to be a while loop, really, really similar to the other while loops we're doing because it's going to go exactly the same number of times as I have objects, elements in my array. Oops, input counter is less than the number of players. Input counter plus plus. So now I know that my while loop here is going to do exactly what, it's going to run exactly the right number of times. So now I'm going to ask the user to type in scores, and I'm going to scanf them and write them into the list of scores, into the array of scores. So printf please type in player someone's score. And that's going to be the input counter. And then I'm going to do a scanf. And in here, I'm going to expect an integer. And I'm going to put that into scores input counter. So you can see how this stuff is kind of handy, because what I'm actually doing with that scores input counter is I'm saying to scanf, here's my array, here's how far into the array you go, this is where you write that information. So I'm saying the user's going to type in an integer, please store the integer in my scores array in a specific position. So this loop now should be able to run exactly the right number of times, take score, and then display what those scores are using this function. And then we're going to loop through and find the highest current score out of those and report it. So let's save this compiler and run it and see what we get. Let's save that, Control S, using my up arrow to get my previous commands for my compilation. And then I'm going to run the scores. Okay, hit me with numbers. What have we got? 5, and then 6. 99. 2 million. 1, 2, 3, 4, 5, 6. Yes, sold. You paid too much. Okay, so I have an inkling for who might win this game. I don't know. Although, if we add a few more zeros, we could overflow this integer and end up with a massive negative number. But let's leave it like it is for now. Is that 2 million or 200,000? That's 2 million. Cool. So now not only do we have looping for displaying, we have looping for finding information out inside something, and we have looping for input. I have a few, I've got a couple of minutes, but I think I'm going to wrap it up here. But what I want to give you is a couple of challenges for things that you might want to do with this. So we didn't look at getting the total score. So can you edit this code to also print out what the total score was of all the players? Can you do it to find the lowest scoring player as well as the highest scoring player? And another bonus, can you take some of this code out of the main and put it into a function and have it still work? So those are some things you can play around with if you want to. All right. I will see everyone next week, unless I do a live stream before then, but I'll let you know when that's going to happen. Yeah, hey.
What do you play this score array without assigning anything?
Yeah, so that score array is something that the function itself is going to use. Yeah. And it's created from what gets given to the function. So every time the function runs, it's going to get something as its input. And that input's going to come from this program and get passed into the function. So whatever was in that goes into there. And so every time this runs, score array might be a different array, but it's going to be whatever was given to it when it was called by name.
Then why can't we just put these scores into this score array?
Because scores only exist within this context here, and not within the context of the function.
Oh, so you put the function outside the main?
Yeah, the function's outside the main, so it doesn't know what scores is. But we're going to give the function scores, but the trick is, when the function runs here, it's going to get scores from a particular point in time. If we call the function again later and the scores have changed, then we don't want it to have the same scores. We want it to have whatever the scores are at that point in time. So later on, it's going to get a different value for scores passed in. So each time we run the function's going to jump out of the main at a particular point in time. And that point in time means that whatever variables you give it are from that particular time. right?
So you just like assign this integer to the score, whatever score.
Yeah. So this is saying that the thing that the function's going to work with is whatever this was at line 20.
Right.
So if I do scores at line 15 or 16, only some of them are going to have values, and some of them are going to be 0, and so it'll be a different array that goes in.
I see.
Yeah. Cool.
That means we define a function that's the input was the array.
Yeah.
So why we like this, so we don't have to maybe pass a square bracket or just the name.
Yep, we don't need any square brackets because this is the whole array. If we put square brackets after the array like this, we're looking